Hello students, welcome to the course Verilog HDL. In the previous video, we discussed a first exercise on data flow modeling, which is a full subtractor. Okay. So in this video, we'll have another exercise that is a magnitude comparator. Okay. So just first we'll read the question and then we'll see the design and then Verilog description, stimulus module and the simulation output. Okay. So first two slides, it will be question. So read out. A magnitude comparator checks if one number is greater than or equal to or less than another number. That is called as magnitude comparator. It checks the two numbers. If it is its output is either 3, either it is equal, less than or greater than. So when you say greater than, less than, so you can have an idea. So there is a concept of relational operators here. Okay, but still we implement using Boolean expressions. Okay, so we'll continue our question. A 4-bit magnitude comparator takes two 4-bit numbers A and B as input. We write the bits in A and B as follows. The leftmost bit is the most significant bit. That means 4-bit means AB, A of 3, A of 2, A of 1, A of 0, and this A of 0, and similarly B of 3, B of 2, B of 1, B of 0. So this last bit is the least significant, the leftmost bit. A of 3 and B of 3 is the most significant bit, MSB, and this is the LSB. The magnitude can be compared by comparing the numbers bit by bit, starting with the leftmost significant bit. Okay, if any bit mismatches, the number with bit 0 is the lower number. Okay, so question is not stopped here. To realize this functionality in logic equations, let us define an intermediate variable. Notice that the function below is an XNOR function. Okay, so x of I equal to A of I dot B of I plus A of I bar dot B of I bar. Okay, so just read out. Okay, what is meant by that? We'll explain. Okay, the three outputs of the magnitude comparator are A greater than B, A less than B, and A equal to B. These are the names of the outputs they have only have given, and they are defined in the following logic equations. Even the equations also they have given, so no need to do. So just you have to use the operators and do it. Okay. So A greater than B equal to A of 3 dot B of 3 bar A. Okay. So this is the x of 3 A of 2 B of 2 bar, x of 3 x of 2 A of 1 B of 1 bar, x of 3 x of 2 x of 1 A of 0 B 0 bar. Okay, then less than B you have A of 3 bar B of 3, then x of 3 A of 2 bar B of 2, x of 3 x of 2 A 0 1 bar B of 1, x of 3 x of 2 x of 1 A 0 bar B 0. Then A equal to B, it is just a multiplication x of 3 x of 2 x of 1 x 0. Okay, so this is an XNOR function, so that is multiplied here. Okay, all the four. Still it is not completed. So finally, write the Verilog description of the module magnitude comparator, instantiate the magnitude comparator inside the stimulus module, and try out a few combinations of A and B. Okay, so this is the question. Okay, so what is meant by a comparator here? Okay, so this is, so these are the four equations you need to write as an assign statement. Now answer is simple. Okay, so wherever I is there, so now you have to substitute 0 1 2 3, x of 0 x of 1 x of 2 x of 3, because there are 4 are there, right? I is 0 because 4-bit magnitude comparator. So this is already ready made, is given. So wherever complement is there, you will use negation. Wherever multiplication is there, you will use and. Wherever plus is there, you will use the or. Okay, so answer is there ready. Okay, but this question same way if they ask to design, okay, or design a magnitude comparator, so you should know the here in this exercise we try to tell you the complexity involved in data flow modeling also we are trying to explain. Okay, so that is the idea. So just try to explain what is meant by a magnitude comparator. Okay, so just simply first they have asked 4-bit, so 4-bit is a very complex, so we'll start with 2-bit magnitude comparator. Just try to give you an idea. So if 2-bit magnitude comparator means same numbers I will take A, B. Okay. So A and B, and the three signals will be A equal to B, A less than B, A greater than B. Okay. So I call that as EQ, LT, less than, and then greater than. Okay. So any order you can add. So these are the three outputs. Okay. So that is your magnitude comparator. Okay. So just to show you its IO diagram, so you write down. Okay. So first one is IO diagram. So write it here, 2-bit sorry, just write it magnitude comparator, because it can be extended to any number of bits. Okay, so this is the, I will not write completely. Okay, you complete this magnitude comparator. Okay, and it is having two inputs, A and B. Okay, I will show you a general. Okay, then it will have three outputs: equal, less than, and greater than. Okay, you draw it neatly, so it is very difficult here. Fine. So this is the magnitude comparator. So AB, how many combinations it will? So if it is a 1-bit comparator, so now I am considering 1-bit comparator, means A and B will take single value. That means it will have 0, 0, 0, 1, 1, 0, 1, 1. Okay, so 1-bit comparator means A and B can take only two values, either 0 or 1, B also 0 or 1. To form this combination, we have written 0, 0, 0, 1, 1, 0, 1. So now if you compare here bit by bit, okay, so 0, 0, both are equal. So this equal output will be 1 and these two will be made 0. Clear? Okay, so then 0, 1. So when you compare this, is A 0 is less than 1? True, right? So for less than 1, you have to make it 1 as the output, and this one you have to make it as 0, other two 0. At a time, any one of the output will be high. Okay, then 1, 0. So A is greater than B. So that means this is 1 and other two will be 0. Then 1, 1. So what is 1, 1? Again equal. So equal will be 1 and these two are 0. Okay. So now if you write the expression for this, so what you will get? Equal here 0, 0 and 1, 1 case 1. That is nothing but this is an XNOR function. Okay. So this is an XNOR function which is nothing but A bar B bar plus AB. A XNOR B. This is the output for equal. Okay. One expression is over for equal. Similarly, less than, so it is A bar B, just one product, A bar B, and for this it is A B bar, A B bar, and for this A bar B. So remember this. Okay, so this will extend. So always this is the first number, A bar B or AB bar, that is the greater than and less than. So these are the three simply you will do. Okay, even you can do in very behavioral, very simple using if else statements. Okay, but now it is three expression here. XNOR, you know, XNOR gate is there available, XNOR operators, not of XOR you can use, and this here you can use A bar B, AB bar. So 1-bit comparator is ready. So now this, if the same thing, if you extend it to 2-bit magnitude comparator now. Okay, so what will happen? So just note down this. I will erase this. Okay. Okay. So if we extend this to 4 bits now. Okay. So the same IO diagram will holds good, but now output also same 1 bit. Okay. So whereas A and B now 2 bits. Okay. So that means what? You will have A of 1, A of 0. Okay. Similarly, you have B is 2 bits, B of 1, B of 0. Okay. So this is the input you got. And now you have the truth table same way, equal, less than, and greater than. Three outputs are there. So how many combination will now? Because of 2 magnitude comparator, 2 to the power 4, 16 combination came. 0, 0, 0, 0, 2. Okay, I will not write everything, so just giving an idea to you. Okay, 1, 1, 1, 1. So till here you have to compare. Comparison is very simple now. You have to compare completely A bit. Okay, so 0, 0, 0, 0 you have to compare. So this is 0, this is 0, equal to sign is 1. Next, if you came 0, 0, 0, 1, so this together will compute it. Okay, so this is 0, this is 1. So you'll have many combination of less than, many combination of greater than, many combinations of equal to. So equal to you will get in only few cases. Which are those few cases? 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. Only 4 cases of 1 you will get. Okay, and remaining out of 16, 12 combinations, the 6 will be less than, 6 will be greater than. So like that you will have a pattern. Okay, so now they are asking in this exercise 4-bit comparison. So you imagine the complexity here. Okay, so A itself of 4 bit, So you imagine, okay, a of 3, a of 2, a1, I will just write simply, okay. So this is 4 bit, and now this is b, okay, b3, b2, b1, b0, okay. So that means what it is, 0 0 0 0 0 0 0 0 to 1 1 1 1 1 1. How many combinations? 2 to the power 8. What is meant by 2 to the power 8? It is almost 256 combinations, right? 256 combinations, and you are getting here there are 8 equal, and then remaining or less than, greater than. When you get such a big truth table, even you could not draw it in a single notebook, right? See the complexity. So that's why they have not given you to design, they have given the expression just to make an exercise of using the operators, okay. But I am explaining here extra. So what is meant by magnitude comparator, and as the complexity is there still in data flow modeling. Imagine this, if the same thing is implemented in gate level modeling, it is too difficult, okay. So for that kind of things we are going for next module, okay. So it is a giving the foundation for next module, okay. So what is the complexity is there in data flow modeling. So this the same thing we will try to implement in behavioral modeling, that is the third style of or higher level of modeling, Verilog HDL. So there we will do it in a very simple manner, okay. So just we'll use the operators, relational operators, a less than b, a greater than b, okay. So there we will do that, or if else statement we'll use that, okay. So relational operators we could not use simply, right? So along with that we require the behavioral constructs, that's why it could not, okay, do it here, okay. So now understood, hope you have understood this, okay. So any bit, so 4 bit, 8 bit, like that it will come. So only 3 outputs you will have, equal, the, greater, okay. So now for your, you can do the exercise, okay. So how it will come, so that's why they have mentioned here intermediate variable. Seeing the pattern, they only have given the intermediate variable, this is x of I, okay. So which is nothing but I told you in the very first table, right? There will be XNOR function will come, right? That's why this function is done it for now, uh, because all the combination of XNOR you are getting one, okay. So that's why it is xi is written, okay, for the sake of writing here a equal to b in simple manner, okay, just a product. So a of 0, b of 0, a of 0 bar, b of 0 bar, like that it is written, okay. So that is the idea, okay. So this is the intermediate variable, this you have to make 4 lines now, 4 statements, and that you have to write assign. Then these 3 outputs you have to write the same one, you have to write it in Verilog description, okay. So just to give you idea what is magnitude comparator, that's why I took that much example and did it, okay. Fine, you can do it more exercise, and you can find out is the same expression is going to come, okay. Definitely it is going to come this same only, okay. So now just we'll write Verilog description for this, okay. So Verilog description is very simple, I told you. Module magnitude comparator, name of the module, a b are the 2 inputs, and a greater than b, a less than b, a equal to b. So these are the 3 outputs I told you, okay. So this is completely one, okay. So it is the name they have given, a underscore gt underscore b, okay. A underscore LTA underscore B, A underscore EQ underscore B. These are the 3 outputs, 1 bit scalar, and AB will be the vectors because 4 bit, no, depending on the comparator we use, okay. 2 bit we will use, it is a 2 bit vector. 4 bit comparator it is 3 is to 0, like that, okay. So that's why output here all 1 bit, A greater than B, A less than B, equal to B, and input is vector of 3 is to 0 AB, because A1, A3, A2, A1, A0, B3, B2, B1, B0. So 4 bit it should represent. Okay, clear? So now to declare the intermediate x of I, we have used a wire here, wire 3 is to 0 x. So they have shown no x of I, one intermediate XNOR function. To implement that, we have used x here. So it will take now 4 values. X of I place, it will be x of 3, x of 2, x of 1, x of 0. If you implement that, you will get a of 3 and b of 3, or a of 3 and not of b of 3. Just you see, whatever complement is there, we have used negation. Wherever multiplication is there, we have used ampersand. Wherever plus is there, we have used logical or. Okay, you can use the double or single or, it will give the same result here, okay, in this case. So then we have 3 statements of output, greater than b, less than b, equal to b. The same statement is written over here, okay. So wherever I have multiplication and I have used Wherever negation I am having, negation operators I have used, and then I have used the OR operation. See that a of 3 b of 3 bar, x of 3 a of 2 b of 2 bar, x of 3 x of 2 a of 1 b of 1 bar, and then x of 3 x of 2 x of 1 a naught b naught bar. So this is the a greater than b. Comma is used, that means you could not use, no need to use assign three times. Even you can do, if you put a semicolon here, you can use the assign. You have to compulsorily use the assign here for each line. Next, second, a less than b. So just you see this pattern here, a of 3 not b of 3 was there, now it will be not of a of 3 b of 3, because which is greater than is there, it will be not there, right? So exact opposite will be there. Okay, so a of 3 bar b of 3, then x of 3, here you also see the change, a of 2 not b of 2 is there, here see a not 2 bar b not b of 2, x of 3 x of 2 a of 1 b of 1 bar was there. So only if 2 bits you compare, here c becomes, here a of 1 was there, here b of 1 bar, here not of b of 1 was there, here b of 1. Okay, similarly x of 3 x of 2 x of 1, then here also a naught bar b naught is there, here a naught b naught bar is there. So like that combination you will get, and these are the intermediate. X indicates the intermediate. Finally, a equal to b is just the product x of 3 and x of 2 and x of 1 and x of 0. Okay, nothing but the product of these four expressions. Okay, you could not write it all these, right? So that's why they have made intermediate variable and simplified this expression. Okay, so in case if you miss here one of the ampersand, one bracket, or one of the or anything, so the program will give you the semantic error, syntax error also sometime. Okay, see this complexity is getting more. Okay, so if you imagine some complex circuit, so complexity will arise still in the data flow description. Okay, compared to gate level, so it is more concise. Okay, so hope you understood this program now. So now for that 256 combination, we could not do it for all the combinations, right? That's why few combinations we will take. Okay, all the combinations we could not check. Okay, 256 combinations will come. It is difficult to do the stimulus module, so just we will write it for few combinations. Okay, stimulus module same way, module test register input whatever is the register 3 is to 0 a comma b, and output is yr a greater than b, a less than b, a equal to b. Same thing as used. Design we have calling magnitude comparator was name of the module, then its instance name, and then each of the variables are assigned connecting ports by name. That concept we have used here, a less than b, a equal to b. Okay, 5 signals are, then we are giving this few combinations, initial, begin, and all. Not all the combinations we are not giving. So see here, initially 0 and 1 we are using. Okay, so that means 0 0 0 0 and 4 bit 0 0 0 1. So this combination we are using. Okay, so what is the output of this combination? It is not equal and a is not greater than, a is less than, right? So a less than b is 1. So first case you can note down here only. Okay, so next slide I will show you that simulation output. A less than b is 1. So 4 bit we are comparing here. So 4 bit we are comparing. Second case we have taken 0 and 0, both are 0. So what is the expectation for both 0? Definitely it is a equal to b is 1, right? So the whatever combination we have, a equal to b is 1. Next you have 1 1, again you have 1 1 combination, all the 4 bits are 1 1, again the output is equal is 1, right? So a equal b is 1. Okay, next combination I have 0 1 0 1 1 0 1 0. Okay, so 0 1 0 is equivalent is 5 in decimal, right? 1 0 1 0 means 10, 5 is less than 10, again a less than b is 1, right? So this is how you compute the result. Next 1 0 x1 1 0 x1. So bit by bit it is comparing. So it is 1 0 x1 1 0 x1. Okay, the result may be x here. Okay, because you could not predict what is the here it may be both 1 or both may be 0, or it may be this 0 this is 1, or this 1 this is 0. Anything can happen, so result may not be clear. So it will be giving uh, equal. Okay, because you have only 3 outputs, so it can have equal. Okay, or it is x will come. Okay, just will verify. So 0 1 1 1 x 1 1 1. Okay, so the result it will use some this one. Okay, so we have to see here x, we have to give value, either it will be 0. What will happen if both 0 0 here, it is equal, right? If this is 0 1, so 1 0 0 1 1 1, so then it will be less than. So if it is 1 0, then it will be 1 1 0 1, so the a greater than 1, so 1 1 a equal, so all the four combinations chances are there. Okay, so that's why it is difficult. Then here also 0 1 1 is there, x 1 1 is there, but in this case, so only one side it is x is there, so either it can have 0 or it can have 1, right? So if it is having 0, you say it is equal, if it is 1, it is less than. Okay, so such output will give always result x. Okay, so this is the thing. Then initial monitor, just monitoring the output a b c, whatever value you have given, and a greater than b, a less than b, equal to b as written. Okay, so this is the stimulus module as we are writing in all the cases. Okay, okay, so just we'll see the output here. See here, all the cases it is x. Okay, so what combination it will come? Fine. 0 0 0 1, first case it is a less than b is 1, 0 0 a equal to b is 1. Like next one was there, so it is so 4 bit 1 was there, it is not 1 1 1 1, 0 0 0 1 0 0 0 1 combination. A equal to b is 1, then 0 1 0 1 1 0 1 0, definitely a less than b is 1, so that's why a less than b is 1. Next 1 0 x1 1 0 x1 was there. Okay, so it is giving all the three is x. Okay, so you could not predict the answer here. Okay, all the three is x. Then here 0 1 1 1 1 1, so here only two combination. If it gets 0 here, it is equal. If it is 1 here, less than, so greater than does not play any role, that's why it is made 0 here. See here result. Okay, and remaining 2 is made x. You could not predict either one, it will be 0 or 1. Okay, whereas a greater than b is not possible here. Okay, x if takes 1, it will be less than, if it takes 0, it will be less than. Greater than p does not play any role, that's why it is kept 0 as it is. Hope you understood this. Okay, so this is the magnitude comparator. So in the next one more exercise I have, that is the 4-bit synchronous counter. So we'll discuss in the next video. Okay, so go through once again the design, and if you have time, you can, if you are interested, just you can 256 combination you can write and see the complexity of getting an boolean expression out of that. Okay, so that's why we'll be looking at another style modeling. Okay, that is behavioral. That is our next module or next unit topic of interest. Okay, so we'll have one more exercise on counter also in the next video. Thank you.